Hello, we are the group number 4 and we will expose you our project Design, Simulation and Validation of a Centrifugal Pump. This is the index and the order that we will follow during the presentation. As an introduction to the topic, centrifugal pumps are turbo machines used for transporting liquids by raising a specific volumetric flow to a specific pressure level, are also crucial elements in many industries. In fact, according to data of the United States Department of Energy, 20% of the demand for electrical energy in the world is supplied by pumping systems. On the other hand, CFD, computational fluid dynamics, has become of extreme importance during the design of centrifugal pumps since it predicts the behavior of fluids inside it before it is even constructed. These are the objectives of our project that can be summarized in performing the reverse engineering of a centrifugal pump through CFD simulation.
The design of the centrifugal pump was based on the unidimensional flow law, Augury's method, and the requirements needed for the pump, which were an angular velocity of 3,550 rpm and the head and the flow at the best efficiency point. Some of the parameters calculated were the impeller diameter, the total number of blades, and the volute diameter, which were 0.165 meters, 6 blades, and 0.286 meters. These and other dimensions calculated were used for establishing the distribution of the blades on the impeller, the geometry of the volute, and create the part of the pump. We can see the results on these figures below. Figure B shows the blade distribution and the form of the volute. Meanwhile, Figure A shows the meridian section of one blade. This section will be important for the next step. The data obtained from the meridian section was exported to inventors in order to start the construction of the pump. The impeller and the volute must follow the calculation made for the design. Otherwise, the performance of the pump may be affected. After the parameters were calculated and the creation of the impeller and the volute on the inventor, which are shown in this diapositive, the final step is to assemble these parts. Furthermore, a suction pipe system and an outlet nozzle were added to the design. The selection of the appropriate models provides a better prediction of the behavior of the fluids. These are some of the assumptions and physical models chosen. Cape Epsilon. This model was chosen because it contemplates the dissipation rate and kinetic energy due to the turbulent regime, segregated flow. This allows the decrease of the computational time necessary for the simulation. Furthermore, it resolves the equation for velocity and pressure for each fluid. Two-layer all y plus wall distance. The y plus value must be between 1 and 5. This treatment could assure that the y plus is within this range. Otherwise, the results obtained from the simulation could be imprecise. A steady flow. This assumption will reduce the convergence time. Constant density. The fluids are not compressible.
The meshing process was made by extracting the pump's internal volume, and with the custom controls already mentioned, the internal volume was discrete by cells. As you can see on the table, the number of cells obtained was near to the million cells. However, the mesh needs to be optimized to avoid the kind of problem that shows the second image. The size of the cell next to the prims layer has a huge increase. That problem happened because of the restrictions of having only 4 prims layers and 1 million cells. The meshing includes the mesh independence test. For it, 3 different mesh sizes were made. The base one is the mesh already done, and the others are meshes with different base size values. We took the efficiency and the total head and compared them with the time. However, the time has a small change while the number of cells increases, so it's not a big issue for the computational time to increase that number. But as you can see on the first diagram, the value doesn't stabilize, but it seems to stabilize if we increase the number of cells. The second diagram shows a constant value between the curves and the base meshes, but that value changes a lot for the last one, and let us understand that this value is not stabilized and we need to increase the number of cells. It wasn't possible to increase the number of cells because by decreasing more the base size, we just reached the fine mesh. Otherwise, the range of error was important. To get an accurate mesh and solve the problem of the decreasing base size and the big changes between cells and Prim's layers, it's important to make a refinement in some special areas, and we need to add more Prim's layers. In the industry, it's recommended to use a number of Prim's layers between 6 and 10. So, if we use at least 6 Prim's layers, we may obtain an accurate mesh.
Now we are going to discuss our results. First of all, we have the wall Y+. We can see that the water wall Y+ is greater than the mineral oils wall Y+. This is given by a greater Reynolds number that indeed comes from the higher viscosity on the mineral oil. Also, both average wall Y+ values are below 5, which is a good sign, meaning that the turbulent boundary layer is within the viscous sublayer, meaning that it's governed by viscous effects and is a laminar regime.
In this sense, we can see that near to the impeller size, there is cavitation, which means that the absolute pressure in that point of the impeller is lower than the saturation pressures of the fluids. In the BP, we can see that this phenomenon also occurs. This can be explained by the Bernoulli's law, which tells us that the increase in velocity implies a reduction in the pressure. On the other hand, during the simulation, the pressure outside the volute was taken as a reference point, which explains the negative values.
Concerning the speed profiles produced by the simulation, a higher speed can be observed in the areas close to the impeller, as expected. Besides, a speed close to zero is evident in the walls of the bullet. This is explained by the geometry made in which is assumed that there is no slayer. This occurs in every simulation, regardless of the flow rate. How we can observe. It can be evidenced at the best efficient point compared to shut-off. This is because a higher flow will translate into a higher speed, given its definition as long as certain transversal zone is maintained. We can observe that it should be noted that a high flow rate is not always good, as an inadequately high flow rate could cause cavitation. It's important to operate pumps with an optimal flow rate to avoid this phenomenon. In this case, best efficiency point. Given the properties of the fluid, a higher speed is expected in water, due to its low viscosity compared to mineral oil, which will move slower due to its high viscosity. Like this. Especially in this scene, it's possible to observe that the fluid has a kind of recirculation in the area of the pump dome. This event can be attributed to the geometry in this area, since the resulting abrupt change in geometry. However, it may be the centrifugal force that the impeller imparts to the liquid when it enters the rotating zone must also be taken into account. It drives the liquid towards the wall of the bullet, causing a recirculation in the middle of the discharge zone. Decreasing rotation speed, you can avoid this phenomenon, this problem. The following give recreate that occurs in the pump, the phenomenon of recirculation. It's important again propose decrease the rotation speed and improve the geometry in the tongue of the pump. This was for the water, this is for the mineral oil.
Following the reports given by the CFD software, we can plot our operation curves. For the total head, we can appreciate that the mineral oil always gives a lower head than the water. This is because the mineral oil has a higher viscosity, so we can conclude that at a higher viscosity, the lower the head. For the efficiency, we can see that the mineral oil also gives a lower efficiency than the water. This is because the brake power for the more viscous fluid increases more rapidly than the hydraulic power as the viscosity increases. For comparing our results with the manufacturers, we use the root mean square method. For the head, we can see that the behavior is very different. This is due to the poor mesh generated and the lack of an experimental approach, giving us a very high root mean square coefficient of 40.43. On the other hand, we have the efficiency plot, where the behavior is almost the same, but the values are considerably lower. This is also due to the lack of an experimental approach and the limitations in the meshing. However, the same behavior gives us a lower root mean square coefficient of 0.16. To round this work up, we propose 5 conclusions. First of all, the obtained mesh was not optimal because of the parameters used for its construction. If we can increase the number of cells and the previous layer zones, the mesh will be better and closer to the ideal mesh. Also, the mesh independent test was not ideal because of the same problem. The parameters were too restrictive and the base size was no longer sufficient for formulating a very rigorous MIT test. Also, the wall Y plus is not a good indicator for the mesh quality because we know that our mesh was not very high quality, although we are having very good values for the Y plus. Also, the viscosity of the fluid has a noticeable impact in the pump's performance, as we see in the comparison between the water and the mineral oil. And finally, the simulations presented cavitation in the impeller that can be reduced or even can be completely get rid of if the rotation and the geometry is tweaked. It's recommended to lower the RPMs and to make a very refined diffuser. Thank you for your attention.